Yeah, so this is like a perfect storm of things coming together, I feel like. So Zeke, you're going to talk about your helical antenna and tracker?
The whole tracker itself.
Great. Well, I'm going to just let you go to it. You want to come up here, or are you back there? Okay.
Hello, everyone. I'm Zeke, and I made an affordable, portable Orbital Desktop Satellite Tracker. And so in December of 2023, I heard about the Oregon State Science Fair. And because I heard about it in December, that meant that I only had 3 months to complete my project, a 3D printed desktop satellite tracker. Now, why satellite tracker? Well, that's because of my previous project, where I made a huge satellite tracker to contact the International Space Station using ham radio. Okay, so why 3D printed? Well, all of my other desktop-sized satellite trackers were made out of Legos, so I wanted to try something new. But the problem was, I did not have a 3D printer, and I did not know how to use one. So I bought myself a 3D printer, and using it had a steep learning curve, but I was able to make this a fully functional desktop satellite tracker that can track satellites, planets, and stars. So today I'm going to talk about some of the features and how it works and go into detail about all the parts, and then I'm also going to share a few tips that I learned along the way. So let's jump right in. So the first thing I designed was the 3D design model. So I designed this in Tinkercad, and as you can see, here are all the parts for it. And these parts in this area have to do with the planetary gear system. And so the planetary gear system is what moves theta, which moves the antenna, this top part, left and right. And from now on, I'll be using theta to mean moving the antenna left and right. And so the way the planetary gear system works is the motor drives the lower stage, which drives the upper stage, which drives theta. And then on the top here, connected through a flex board, we have phi, which is just a worm gear system powered by that motor that moves the antenna up and down. So as you can see, I made a whole lot of 3D print attempts, and so part of the reason of this is because the teeth on the prints were so small, and it was kind of hard to get that accuracy that I was needed to be able to print that. So if I were to do this again, I would use bigger teeth so I don't have to worry about accuracy. So now onto the programming side of things. And so I put together on a little breadboard a magnetometer, which is basically a compass for measuring theta's position. I have an accelerometer for measuring phi's position. I have an LCD screen for selecting satellites and displaying telemetry. And I have my ESP32 microcontroller, which controls it all. So this is like the step before I put it onto a circuit board. And so this is the real circuit board, and I just wanted to talk about some of the differences on this board. And one of the main differences is these 3 prongs. And those prongs, each on the bottom, have 4 contacts. And those contacts press onto the circle board on the next slide, which gives power to our flex board. And so the serial connection is just to be able to talk to it and do extra things like download satellites for now. And then we have our GPS module for getting extremely accurate positioning for tracking those satellites, planets, and stars. And then we have the LCD screen, which allows you to be able to track things. And then the buttons control everything. So here's the circle board, and notice how the contacts each press onto one of those 4 rings. And so the reason for the circle board is it's basically a slip ring. And if we did not have a slip ring and I just used a wire, the wire would twist all up. So the circle board allows it to spin forever. And the flex board connects into a FPC connector, and it just shoves right in there. And that is how we get power to the flex board on this slide. And so notice how we have teardrops here. Now teardrops they're there to mainly prevent what I like to call micro cracks. Now micro cracks are when you bend the circuit board one way and it doesn't connect, and you bend it the other way and it does. So teardrops, and that red part is where it is likely to break. So teardrops allow you to angle into that and gradually slope into the big pad so that you don't want to break at that hard change. And so now that we have that, that's where the teardrop is on the actual thing, and it's really easy to add teardrops in KiCAD. Just select add teardrops, and it adds them everywhere, so you don't have to worry about that. And then the theta motor mount is where we directly solder the motor for theta onto the flexible PCB. And so that will allow it to be able to move. And it will bend all up into that area on the tracker. And then the motor driver controls the theta motor, which is controlled by PWM. And then the magnetometer measures position. And there's the phi motor. It's basically the same thing as theta. And then we have our accelerometer for measuring the phi position. And it bends and connects right into the arrow, which is where the antenna goes. And so these are pictures of the actual flex board, and notice how the motors are directly soldered to it. And this allows me to bend it all up. And I just wanted to talk about some of the problems I had and some of the solutions I had for those problems. So some of the problems I had were the pads would come off where the motors are soldered. I would burn pads or font holes, and I'll get to that in a minute. And so to fix the pads coming off when I would solder the motors, because it would all get bended up, and this is actually version 2 of the flex board, I can widen the copper pore and shrink the cover lay over that so it really holds it in there and it doesn't want to come out. And then I can also, for burnt pads, reduce my temperature. So you just have to minimize your temperature and your heat to keep from burning those pads. So don't go above 250 degrees C when you are soldering the surface mount components, and don't go above 300 degrees C for more than 5 seconds when you're soldering the through-hole components. And so stenciled fonts. And so these are the font holes. And notice how on my V1 circuit board, notice how it's a different color, we have all of these fonts, but notice how there's no holes for the B or the E's, and that's not on purpose. It's supposed to look like that with all the holes. And this is because of the way that they put on the cover lay for flex boards. It's a separate piece, unlike traditional circuit boards, and so anything that's not connected to the main piece of cover lay will just fall off. So what I did is I just used stenciled fonts, which connect the holes in the letters to the main piece of cover lay, and it works great. And then the holes don't fall off. So now I just wanted to talk about how easy it is to solder these teeny tiny components. These is the magnetometer and accelerometer. And these ended up actually being the easiest components to solder on the entire flex board. And the reason for that is, and they have 0.25 millimeters between their each and their pads. And so the reason that they're so easy to solder is because they come with solder balls on each of their pads. And that allows it to nicely snap into place. So all you have to do is put the smallest dab of flux paste onto the pads, stick the component on there, heat it up, and it will magically zip into place because of the surface tension of the solder. And so if you use any solder paste on these components, that is a huge problem because they're 0.25 millimeters apart, and so they are very likely to short. Just heat them up. So now I wanted to talk about my helical antenna, and this antenna is what allows me to, well, I was going to try to receive signals from this satellite, Orsat-0, but the problem was their low noise amplifier was broken, so they were not able to send the signal to turn on their camera. However, I will be trying again to receive the signal and get their pictures of space from Orsat 0.5 later this year. And because I want to make sure that I can receive that signal later, I want to make sure that it works. So I entered my antenna characteristics into an online calculator, and I got these results. And the main two things we care about are the things highlighted in green. The half-power beam width, and half-power beam width is just the point at which minus 3 dB. So if we have 15.9 dB straight forward, at the half-power beam width we will have 12.9 dB. And so the half-power beam width is huge at 42.5 degrees. And what a dB is it's like a measurement of gain in a specific direction. And so that's huge. That is an amazing wide gain. So we should be good for the antenna. And 12 dB is quite a bit. We should be fine. And because I am good there, I wanted to make sure my magnetometer is accurate to 42.5 degrees. So I used a compass to measure the accuracy of the magnetometer, and my highest error was 7 degrees off pointed east, and that is way less than 42.5, so we should be good there. And so now that we know my magnetometer is accurate enough, I wanted to make sure my accelerometer is accurate enough. So first what I did is I offsetted it until the level was leveled, and the bubble was right in between those lines. And then I took it, and I rotated it up to I rotated it up to where it thought was 90 degrees, and I measured 14.2 degrees of error when I took a picture of it and moved that arrow. And 14.2 is still way less than 42.5, my half-power beam width, but I wanted to make it even less. So there is actually a way to do that. I can divide the error by 2, and you know how I was offsetting phi over here? Well, I can offset it plus 14.2 divided by 2, which is 7.1, and I can offset it plus that so that we get that 7.1 degree error. And it would be 0 degree error with the level leveled, but now we have 7.1. And then if we move the antenna up to where it thinks is 45 degrees, it will actually be 45 degrees, no error. And then if we move it up to where it thinks 90 degrees is, we'll have a negative 7.1 degree error again. And 7.1 degrees is even less than 14.2, so we're even better there, way less than 42.5. And so now I'd like to thank all of these organizations for helping me and supporting me on my project. And go subscribe to my YouTube channel and check out my GitHub for more links for all the code that I used for my desktop satellite tracker. And I will be doing a demo outside, so go check that out. If you have any questions, that would be a great time to ask them. Yo. Yeah? Okay. Thanks. Here.
The only change I would suggest is instead of using the words phi and theta, use the more standard terms azimuth, elevation. Azimuth, elevation.
Yeah.
That's more standard terminology instead of using phi and theta.
Yeah.
Nice talk, though.
Thank you. I was very intrigued by your choice of using a planetary gear system to drive theta. Could you talk more about that, why you decided on that, and what alternatives you might have considered?
So the reason I did a planetary, here, let me back up to that slide. Hit the wrong laptop. So the reason I did a planetary gear system is, one, because I've never done it before, two, because it looks really cool, because there is double stage, so the bottom stage is moving really fast and the top stage is moving slower, and three, because I wanted to try something new. So I recently learned about a cycloidal gear system, and I think that could be another cool option for it. But this is what we have right now, and it seems to be working. However, it does get stuck a lot.
Would it even be possible to use direct drive instead of going through a gear system? That was the question.
Probably yes, but going through a gear system allows it to look better.
Yeah, Bernie.
And make it stronger.
Thank you. I was a little surprised at how large of an error you got in the phi, in the elevation. I wonder, did you use only a single-axis accelerometer? Did you intentionally use a lower-grade accelerometer because you knew that you had a large margin for error? Would you discuss a little bit about that, please?
So in the data sheet, this is like one of those components that's like used in phones. And so in the data sheet, it said that it would be accurate to like 1 or 2 degrees. And so I did not calibrate the accelerometer. However, the magnetometer was calibrated, and it was still supposed to be within 1 or 2 degrees, but the compass I was measuring it with was a phone compass, so it might not have been accurate.
Was the accelerometer one-axis or three-axis?
It's a 3-axis accelerometer. Okay. Oh, we only use one of the axes, though.
Any other questions? You know, this is a really interesting project. It's too bad there's not like a company or something that would sell it for you, or I don't know. I'll have to think about that one. Yeah.
I'll sell it.
So could this be a crowd supply kit? So when we have ORSAT 1 up and where people are making the handheld ground stations, they can also have one of your automatic ground stations?
Yeah, so I'm planning to sell this as a kit, and one of the main reasons is because I wanted to be able to receive signals from ORSAT, and so an antenna goes on top of here, and it can track it. And so this could be an ORSAT kit that people could build and receive pictures from.
Awesome. And the ORSAT 0.5 satellite that you just mentioned, I believe Andrew just handed that off, I heard today, 2 weeks ago, for launch. So when's launch? July 10th. Okay, so coming up. So yeah, that project is really ramping up, and it's awesome to see people like Zeke interacting with it and building on it. Any other questions? Okay, well, thanks again to Zeke and to the Corvo team for their support. This is great.